Hello, everyone. The time is 2:49, and we are going to begin around 3 o'clock as usual. So if you're watching this in the future, you can fast forward a little bit. But how's everyone doing today? See, I'm going to be right back actually because I need a refill of water. So we still got about 10 minutes, and so I will be right back. All right. All right, gotta stay hydrated on warm days. But my husband and I can't seem to agree over the thermostat. I'm like boiling hot, and he's like, "Let's turn the heater on to 69 degrees." I'm like, "No, it's like summer now. Let's not turn the heater on." I think I might just try to completely deactivate the heater altogether. But then if it accidentally gets cold outside like it does in Seattle, won't be able to turn the heater on as easily. But in any case, so today we're going to be talking about glaciers. We're also going to talk a bit about, very briefly, Lake Agassiz. But even more, we're going to be talking about the Missoula floods and the channeled scablands just a tiny bit, and J. Harlem Brett's at the end of lecture. It's stuff that's Lake Agassiz is in your book, but the other stuff isn't in your book, and it's a local story, which is why I like it, and also it's an underdog story, and I love underdog stories. Not that I'm necessarily about conflict or anything, but I really do appreciate it when, there's an underdog who comes out and, really proves themselves. I think that that's kind of cool stuff. So we're going to talk just a bit about that. But yeah. How's everyone's week going so far? Got a few of you here. I helped a friend move last night. I got home. I was helping them move from Mount Lake Terrace, Linwood area to basically Fife, where Wild Waves is and stuff, or Enchanted Village. So that was my evening. Got home super late. All right. Just quiet people here today. Nobody wanting to hop in the chat. So, for the couple of you who are here, if you're willing to hop in the chat and maybe say so one way or another, I try to make your previous exams visible so that way you guys can go back and review them. I don't know if I was successful or not, because I read some stuff online about making exams visible, but it wasn't quite clear to me if doing these things meant that you guys were going to be able to see your past exams and feedback that I've given, because I actually took the time to write comments on these, on individual questions on your exams, thinking that I would be able to make these visible to you guys. And now I'm not so sure. But if anybody is willing to go over to Canvas and take a look and see if you can see your past exams now, and let me know if you can or can't see them on your end, that would be great. Because I can't tell. I think I did it, but the websites weren't very clear. I was like, does this mean that they can see it? Yes, we can. Awesome. I was like, does this mean you guys can see it like while you're taking the exam and like your feedback after you submit it? But awesome. So hopefully you guys can see the feedback that I left you too on questions where maybe there was, like, if you put in something that was misinformation or didn't seem quite, that seemed erroneous, that might need some clarification. I made some comments there on a number of exams. And everyone did really well on the last exam on the question where I showed you some housing properties and asked you guys to list the geologic hazards associated with that property. I was so happy that you guys did really well on that. And spoiler alert, there may be future questions on our midterm that show you properties and ask you to identify potential geologic hazards with the property. They might not be landslide questions. They could be other related to other geologic hazards that we've studied and we've talked about. Yeah, so make sure that you like go back to like the earthquakes chapter, the volcano chapter, and like rivers and streams, and mass wasting as well, the landslides and such, and make sure that you understand how to look at something and be like, oh, that is probably prone to these hazards that particular living in that particular area is. So let's see if there's any other announcements. Oh, on the question, there was another question on the most recent exam where I asked if geoscientists, volcanologists can predict whether or not an eruption is occurring. And that's kind of like a bit of a gray answer there. It's like kind of, sort of. It's not an exact science yet, but scientists can tell when something is up. And as that activity becomes more frequent, the chances of an eruption increase. And so they sort of can-ish. Can we predict earthquakes? Absolutely not. Not at this time. Hopefully someday we can. But so volcanoes is a little bit easier because we can usually tell when something's on the move underneath the volcano. I heard that Yellowstone's gotten kind of a bunch of earthquakes in the last, I'm not sure. My husband was telling me it because he actually reads the news, unlike me. I watch YouTube occasionally, though, for news. But my husband was telling me, I guess, that people are freaking out over Yellowstone because there's some earthquakes happening. But, yeah, hopefully, I don't know that that's necessarily cause for alarm. When is it time to be anxious? The time to be anxious is when the volcanologists are anxious. When is the time to really be concerned? When the volcanologists tell people to evacuate. That's when you really start to be like, oh. So, but there's a great saying that Yes, my shirt is a Mob Psycho 100 shirt. I love that show. I have some stickers too that were randomly in this room on the shelf next to me at the start of the quarter, and they've just kind of been living here. This has kind of like been our storage room for like stuff that we're like, I don't know what to do with this stuff. So this was already in here amongst all the other storage items. Mob Psycho 100 is probably one of my favorite animes. Might be, which is weird because normally I like rom-coms, romantic comedies. And Mob Psycho 100 is not a romantic comedy, but it's so good. So if you find yourself with some spare time during quarantine, highly recommend. 10 out of 10. But yeah. So there's only a few of us. I want to kind of wait to see if some more people will tune in. Maybe just 2 more minutes. But how's everyone doing? Let's see. For whoever was the most recent to tune in, exams are now available to view, so you can view your previous exams now. Hopefully that is helpful to you guys. I left a lot of comments, so go ahead and check those out. Everyone did pretty well in the exam too. Like so much better than the last exam, and I'm so pleased about that. Like everyone's scores improved a lot, I think. Most of the scores, the average for this exam, I think was probably about a B-, which is normal for my classes. Having somewhere between a B and a B- being the average. And then of course there's usually some A's, there's some C's. And normally I also have grades that are like D's and F's. But I don't think we even had like any D's or any F's. And quite frankly, I think that a C on my exams is still pretty good. So good job, guys. So proud of you. Looks like Alicia and Echo are doing kind of all right, kind of good. I know it's like a difficult time right now with everything that's going on, protests and riots and stuff. I literally live right next to the Alderwood Mall, and they closed a lot of Alderwood because they got wind that people were going to loot the mall, not protest at the mall, but literally just loot the place. So they closed it down like most of Monday, which was concerning because, like, I don't know, I literally live within like walking distance of the mall. So I don't like that kind of activity in my neighborhoods. I don't mind protesting. I think that's all well and good. And, you know, power to you, you know, free speech is awesome. But I don't like vandalism and stealing of stuff. It's not my favorite. I'm all about like, you know, loving people and stuff. And yeah, hopefully progressive change indeed. I definitely think that change is needed, and I also think that like I'm definitely like was anyone around in 03 listening to Black Eyed Peas? You know, I'm definitely kind of like, oh, where's the love kind of person and whatnot. And you know, in any case, here we are. I know that it's tough out there, so make sure that you guys are taking care of yourselves and doing whatever you need to do to, you know, do self-care, you know, staying in touch with friends, you know, engaging in hobbies, studying, working, stuff like that, or whatever self-care looks like for you. So, but yeah, let's see, it's 3:03, so let's go ahead and get started. I will copy and paste the link for y'all to the PowerPoint for you guys. We are going to be starting on slide, what slide number is it? Slide number 31. There's the link for the slides in the comments there. Make sure I get my windows all sorted and whatnot. And so slide 31 is where we're starting. On that slide, there's kind of a recap of what we covered and on Monday. And then up next, we're going to be talking about erosion. We're going to be talking about deposition. And we're also going to be talking about kind of sea ice and ice in the sea. And then also we're going to talk about glacial outburst floods, glacial lakes, J. Harlan Brett's, etc. Stretch goals. So today's lecture might be a bit long. We might go until like a little over 5. We'll see. So, and I have some adorable pictures of Glacier Cat on there as well as the ice climbers. So that picture is from Smash Brothers though. Go ahead and look at the next slide, slide 32, and see if you can identify the different types of glaciers that are in this picture. Let's see. So anybody want to, well, just get in your mind kind of some predictions. Yeah. I think this one's this and this one's this. The two that people usually get confused are the ones on the left. So I'll go ahead and give you some answers and y'all can check and see if you were right. So the one on the, yes, so the one on the top left is actually a continental glacier because it looks like it goes on forever and it covers the entire landscape except for the tip of that mountain. That is probably Antarctica. The lower left photo is a mountain ice cap where it's not as extensive. We can still see, numerous mountains kind of poking out from there. The top right one is, well, the glacier's almost completely gone. But that was a massive cirque glacier, and you can see that beautiful bowl shape that they leave behind. And then the bottom right is a valley glacier. Awesome. So how did you do? Hopefully well. All right, let's talk about glacial erosion, the next slide. Get my slides pulled up. So glaciers erode in land in two primary ways. The first way that they erode is by plucking. So, and it's literally spelled like plucking something. How this works, which is the next bullet point there, is that meltwater finds its way into cracks and it freezes, right? So first some liquid water gets in there, some melt water under the glacier, and then it refreezes. And when it refreezes, it expands and breaks the rock. So meltwater in cracks in rocks gets in there, refreezes and expands and breaks the rock. Next bullet point on there is that basically then what happens is ice lifts up that fractured rock from the surface of the larger rock. So there is a diagram there showing how the ice it'll kind of like at the very base, remember we talked about how it can, under so much pressure, it can melt at the bottom of the glacier and then move around an object and then refreeze. Well, what happens in these cases, right, is you'll have this ice refreezing on the other side and it gets into the cracks though before it refreezes. And when ice freezes, it expands. And then the ice above it is moving along, and it's going to end up plucking and incorporating that rock into its base. The photograph on the right-hand side, you can see some kind of black triangles on the surface of that very smooth rock. These black triangles, that is actually some rock that was glacially eroded, and those triangles there are where the glacier plucked rock, smaller bits of rock from that larger one. I also want you guys to notice, you can't really tell it from this photograph. I wish I could take you guys to the beach where this is. It's at the Cranberry Lake campground right next to Deception Pass, and it's right on the beach. So notice, though, it is very smooth, even though there's a lot of cracks in it and little triangle indents in it. The surface is pretty smooth. I also want you to notice that there's some kind of like linear feature going on here in this picture. So yeah, keep that in mind. We're going to talk about that in a moment. Excuse me. So let's go ahead and look at the next diagram here. Yeah, Cranberry Lake, Deception Pass, such a beautiful place. The next diagram here in the kind of magnified picture of the base of the glacier shows how there is like kind of a rock on the bottom, on the ground, that the water has gotten into, frozen, and has also frozen connected to the glacier. And then if you go to the next slide, you can see how the ice flow at the toe of the glacier is upward, right? We talked about that. So it's actually going to lift that rock fragment from the ground. So let's go ahead and talk about, on slide 39, the next way that glaciers erode. The next way that glaciers erode is by abrasion. If you're a terrible speller like me and you want to know how to spell abrasion, there it is. And notice how below on the left-hand side, we're also seeing a rock on the far left that has some kind of linear features on it. And then there's in the middle some rock that's polished, really smooth, so slick that the sun's reflecting off of it. And then there's also some very finely milled powder in the person's hands there. So let's go ahead and fill in some bullet points for you guys. So that first bullet point there is going to be that abrasion is when you grind rocks, bedrock specifically. And what does bedrock mean? Bedrock is this stuff. See how the rock goes way down below the subsurface in this picture? That's bedrock. It's not just like a random rock on the surface. Abrasion, glaciers grind bedrock and they polish the surface. So the third bullet point there, we're going to define some ramifications, some things that we see produced and left behind as a result of this grinding of bedrock. Rock flour is what is depicted in the person's hand. Rock flour is finely ground bedrock. So yes, that powder used to be bedrock, but glaciers are so powerful that they can grind it up into this very fine powder. Glacial striations are what you're seeing in the left photograph, as well as in that photograph from the Cranberry Lake campground. Glacial striations occur when rocks in the bottom of the glacier get dragged along the bedrock, because this lifting process in all portions of the glacier might not be immediate, especially up towards like the zone of accumulation where the flow of ice is usually downward. Sometimes you get these rocks in the bottom of the glacier that are stuck in the glacier, but they're still surface to surface with the ground below it, the rock below it, the bedrock, and they just go along and they just scrape it up. Sometimes you get that polishing though when a glacier just slides over the top of it and slowly and kind of evenly, as opposed to unevenly, like when you have a rock in the bottom of it, will just nicely polish the surface sometimes because it is such a heavy weight going over it. And then occasionally when that ice gets in there and freezes it, you might get some plucking coming out of it. And that polish is what you're looking at in the middle photo there. Let's talk a little bit more about rock flour because it does some really interesting stuff. Looking at slide 40 there are some lakes which are just incredible colors, unbelievable. Like you've got this kind of greenish blue lake in the top photo there. And then the bottom photo, there's like this kind of teal light blue. The colors in glacial lakes, if any of you guys have been hiking up in the Cascades and seen a glacial lake, they're weird colors. It is because you have that rock flour suspended in the lake. And it's so fine, you can't really see it, but it does affect the way light is refracting in that water. And it causes the water to turn these really amazing colors. Taking a look at some more glacial lakes on slide 41, this glacial, it actually has a bullet point there for you to fill that in. So glacial lake color is caused by, don't drink it, is caused by suspended rock flour. If you have I bet if you have like a life straw or appropriate filtering equipment, you can probably drink it. You need to filter that stuff out. Suspended rock flour. These two photographs are from the same lake. That is Lake Kalchuk, and it is in Leavenworth. It's about round trip and 8 or 9 mile hike. So worth it. It's on the way to the Enchantments. More people have heard of the Enchantments because that's kind of the more wow space. And I have never made it to the Enchantments because you have to have a permit to camp there. And I would not be able to do the Enchantments in a day hike. I would need to camp there. So let's go ahead and look at slide 42. And there in this photograph, you can see these mountains that are pretty smooth. They don't have a lot of angular peaks to them. And these mountains were polished by glaciers that were running through that area. So let's also take a look at slide 43. You see a lot of things labeled here on this landscape. This is kind of a nice, smooth rolling landscape that has not experienced glaciation. You've got this nice V-shaped valley in which the rivers run in because those rivers are down cutting in this highland area. And you can see that on the left-hand side there's a particularly big V-shaped valley, whereas on the right-hand side of the photograph, there's a stream that hasn't down cut as much. The valley is a little bit gentler of a slope. Because it hasn't really incised much yet into the landscape. And you can also see these kind of valleys off the side of the mountain there that don't really have water particularly in them so much right now, but like when it rains, there's going to be like water finding their way into those lower channels and going down to the main rivers. So let's take a look and see what happens when this place experiences glaciation. Slide 44 shows that. This is pretty mature glaciation, actually. that we're seeing. And we see that all the former low points on the mountain are now, sorry if you can hear the airplane, are now filled with glaciers. We also see that the stream valleys have been filled with glaciers. And remember, glaciers are these quiet, slow, massively destructive forces. So the landscape is going to be ravaged by the time this leaves. And slide 45 there shows what this landscape is going to look like after it experiences a lot of glaciation. So the mountain has now been eroded so that there's, you can see some cirques in there, which are labeled. We're going to talk about what, I believe we're going to talk about what a horn and an arête are, hanging valleys, right? And then also like these big giant U-shaped valleys. The valleys that were V-shaped are now U-shaped. So yeah, drastically different. Let's go ahead and fill in some bullet points on slide 46 for you guys. So, is it 46 for you guys? It's not 46 for you guys. Sorry, my numbers have been off this whole time. I must have some slides that I hid in the previous ones. So, but y'all didn't complain yet, so I think y'all figured it out. So on your guys' slide 42, you see that there are these two photographs. One has a V-shaped profile and the other one has a U-shaped profile. This U-shaped profile is a glacial valley. The V-shaped one is not. Glacial valleys tend to be, here's the listed bullet points for you, they tend to be U-shaped. They were previously V-shaped before glaciation. And the third thing about glacial valleys is that they are incredibly large. They are not little guys, they are big. Let's go ahead then, now that we've talked about glacial valleys and kind of the fact that they're U-shaped, used to be a river channel that was V-shaped, and the glacier has made them gigantic now. Let's go ahead and talk about erosional landscapes. So we've kind of changed gears here with these slides. We're moving in, we talked about how glaciers erode, but now we're talking about the landscapes that they leave behind. So they leave those glacial valleys. They also leave behind arêtes, which are these sharp-edged, sinuous ridges. And there is a person standing on one on the right-hand side. And there is also one depicted right below that, where there's this sharp edge. And usually they are kind of long and a bit sinuous. Sinuous meaning that it kind of goes back and forth like this. I think there's a beautiful scene. If memory serves me right, I really need to rewatch Lord of the Rings during quarantine. But if memory serves me right, there's actually this gorgeous pan photo or shot of them actually like in the Fellowship of the Ring walking along an arête. And I saw the movie and I was like, I know what that is. So let's go ahead and talk about a horn that gets left behind. So a horn is it usually forms on the peak of the mountain where the peak used to be. Horns are these sharp pyramid-like peaks. You can see a horn, specifically the Matterhorn, which is the third bullet point on there if you want to type in Matterhorn. The Matterhorn is actually aptly named because it is a horn. So first bullet point there, though, sub-bullet point, is that they are sharp pyramid-like peaks. they are formed, next bullet point, formed by 3 or more cirque glaciers. So basically, you have these usually 3 cirque glaciers forming on the side of a mountain. And if they continue to erode back in, you're going to be left with this point in the middle where these kind of 3 cirque glaciers converged. However, I have also seen horns form from, plenty more than 3 cirques, but you need at least 3. Geometry. And then Matterhorn is that last bullet point because the Matterhorn is so famous. So let's go ahead and look at slide 48, where I can now kind of show you guys some more of these formations in an actual photograph. It doesn't necessarily need to take place over thousands of years to my knowledge, because glaciers really are, while they're slow, they are just extremely destructive, and they do a lot of damage. So I'm not sure that it necessarily takes thousands of years, that it has to, but a lot of the glaciation that we see today did take place over thousands of years, because like glaciers come and go. Usually the planet has gone through these warming and cooling cycles, and where we get ice ages, and then we get interglacial periods, and then we get ice ages. And typically those periods last for a really long time. So yeah. But let's go ahead and take a look at the next slide. I probably misnamed the slide again. Slide 44 for you guys. Slide 44, where you guys see this glacial landscape. What we're looking at, there's like a little label pointing to the peaks, kind of on that far back mountain. And you can see that those small peaks are horns. And then we also see some cirque glaciers, 3 in particular right there in the back. And in between those cirque glaciers are arêtes, those very sharp, sinuous ridges. I never want to hike on an arête. That just sounds terrifying. I'm not too terrified of heights, not particularly, but when there's like not a lot of room to your right and your left, then I start to get a little worried. And I think you have to hike an arête to get to the enchantments. Not my thing. And then below there is a tarn, which is kind of this little lake that's accumulated there. So let's go ahead and take a look at hanging valleys. There is a really beautiful, famous hanging valley in Yosemite, which is depicted there on the left-hand side. And what I want you guys to actually like really look at these 2 photographs before I start filling in some bullet points for you guys, and take a look at where the U-shaped valleys are, and where the drop-off cliffs are. Because what you're seeing there is kind of this U-shaped valley that's truncated and just ends in a cliff, where the topography below it is significantly lower, makes for these gorgeous waterfalls. So let's talk about that. Hanging valley is when you have a U-shaped valley that was created by a small tributary glacier. So a U-shaped valley that's made by a small tributary glacier. And then second point is that these are usually they're not very wide, and they're not very deep. relatively speaking. You guys are looking at those U-shaped valleys that the waterfalls are coming out of, and you're like, that's gigantic, relatively speaking. And then thirdly, these are cut off by a main trough glacial valley. So remember how I've shown you some photos of various valley glaciers that merge into a larger glacier? That's what's happening here, is you've got these small glaciers that are emptying into a much larger glacier. And the larger glacier is going to cut down further. It's heavier. The valley that it's sitting in was bigger to begin with than the ones that the hanging valleys are coming off of. So it erodes much deeper and ends up kind of making this cutoff on these small little tributary glaciers. And that's how you get these gorgeous waterfalls. Let's define a fjord for you guys. So you guys may have heard of fjords if you have watched Disney's Frozen many times like I have. Then you've heard the term. They actually live in a fjord in that movie, and a lot of cruise ships will also, like, kind of in more like Scandinavian areas, they'll take a cruise ship up a fjord, and it's usually very gorgeous. So fjords are these U-shaped valleys that were glacial valleys, glacial troughs, right? So it's a U-shaped glacial valley that has been flooded by the ocean. So previously, this used to be land because all of Earth's water was trapped in, glaciers that covered a lot of the Earth, far more so than today. So sea level was lower. And now as these glaciers have melted and we've come out of the ice age, sea level has risen and has also flooded some of these glacial valleys that emptied out into the ocean. And they're just gorgeous. I would love to go to one. One of those cruise ships would be nice, right? I went on one cruise when I was younger, and I got island fever, actually. But whatever. So let's look at slide 51. Well, my 51, sorry. 47 for you guys. And talk about how glaciers transport sediment. So we're kind of switching gears from erosional landscapes that glaciers leave behind, and we're going to talk about transporting sediment. Why? Because glaciers, erosion means that they have carved out the landscape, but all of this material that they have removed during this erosional process must go somewhere. So let's talk about how that glacier, once it's removed material from these mountains, let's talk about how it gets transported and then how it gets deposited. So you can think of glaciers as large conveyor belts, as kind of like what's depicted below or on the side. So essentially what happens is sediment falls onto a glacier from like the mountaintops or is plucked up from below. So you're seeing on the top picture there an example of material falling onto the top of the glacier, and then below you're looking at how the glacier kind of plucks up stuff from the land below it. And then number 3, this material is transported to the toe of the glacier, and typically it's deposited as an end moraine. And we're going to define what that term moraine means in just a second. So end moraines are not the only place where this sediment is deposited. There's actually a number of depositional features that a glacier can create depending on the circumstances. But glacial moraines are very notable. They're gigantic, and a lot of the sediment that it carries does get deposited in a glacial, in a moraine, an end moraine. So looking at the next slide, talking about transport of sediment by ice, we're also kind of dipping our toes into depositional landscapes here. But moraine occurs, sub bullet point here, when a glacier melts. It drops its sediment as a ridge at the toe of the glacier. So all that sediment is being brought down, and then as the edge of the glacier melts, as ice is, coming to that front where it melts and more is brought and it melts there, the sediment that it's been carrying just gets dropped when it melts, and it forms this big ridge. And we can actually see a diagram of this on the left-hand side, and then on the right-hand side, there's a glacier that's starting to recede, but you can see this kind of dark ridge out in front of it, like a little bit in front of it. There's some flat land left behind, but the glacier sat where that ridge was for quite a while and was melting there at that point and dropping stuff as more ice came down and with more material, and then melted at that line and dropped its stuff. We have some moraines here in Washington, I believe. There is also on page 126 in your textbook a diagram here showing a bunch of end moraines. I have a feeling that the writer of this textbook lives in the Midwest because they focus a lot on Midwest geology. But here we can see the Great Lakes, right? And all the red in this diagram is a map showing where the various end moraines are as glaciers receded during the last ice age. So the farthest down red shows the farthest extent to which the glaciers went forward, and as they melted back, they left a bunch of moraines. Wow, my book is, I wish I had a hardcover. I like hardcovers. So now we need to talk, though, about, so moraine, we just defined the term in general. However, a terminal moraine is specifically one that forms at the front edge of a glacier. So moraines, though, don't exist just at the front edge, obviously, because I just made a sub-bullet point talking about a terminal moraine, which specifically occurs at the front edge of a glacier. Looking at the next slide, we see that there are actually two other types of moraines. There are lateral moraines as well. These form on the side of the glacier because these glaciers are also grinding up sediment from the side of the glacier, right, on the walls. And also material is falling from the walls of the glacier, or the mountains on either side of it. And snow is also bringing down loose material onto the surface of the glacier from the mountain peaks above. And they typically form these very dark lines on glaciers. Moraines do. Lateral moraines are moraines that occur on the edges of a glacier. You can actually go back to the previous slide and you can see these lateral moraines in that photograph as well, or in the diagram as well. And then you see recessional moraines too. You don't need to know that term though. It just means as the glacier's going back. Your book doesn't talk about it. Medial moraines are moraines that form in the middle of a glacier. And how did these medial moraines occur? You're like, well, why would there be an excess of sediment in the center of a glacier? That doesn't make much sense. Well, it occurs when you have two or more glaciers that are merging into one another, and these two lateral moraines that were previously the sides of a tributary glacier converge as the two glaciers as a whole converge together. And that's kind of an interesting way where you can be like, how many tributary glaciers, how many subglaciers make up this glacier, by looking at how many medial moraines there are, because those occur when you get two glaciers that merge together, as seen in that diagram below. All right, so that pretty much covers transportation of sediment by glaciers, as well as we kind of dipped our toes a little bit in talking about transportation of these sediments. You can't help but also talk about moraines, which are kind of more a depositional feature that gets left behind after the glacier. But you can also see them during the transport of sediment. But let's talk very specifically about the types of sediments that get deposited as a result. And then we will talk about what types of features these tend to get deposited as. But first, let's talk about the actual material that gets dropped by glaciers or carried by meltwater from a glacier. So looking at slide, for you guys, got to scroll down on your slide. Looking at slide 50 for y'all, 54 for me, we see that there's the term glacial drift. I don't know, did I leave that? Yeah, I did. Glacial drift. Let's define that. It is an all-encompassing term for glacial sediments. There are many types of glacial sediments. But if you don't want to specify what kind of sediment it is, you just say glacial drift. It's like saying the word dirt or sediment, you know? So glacial drift is just anything that was deposited by a glacier. This includes, now I'm going to give you guys, for this next bullet point, a list of different types of glacial sediments. Don't worry if you don't get them all, because we're going to talk about each one of them. This includes till, erratics, outwash, which is also, I think our book refers to outwash as, oh, I'm on the wrong page, stratified drift, moraines, and loess. We won't talk about loess. It's spelled L-O-E-S-S, and varves. Will we talk about varves? I think I'm gonna talk. I think we talk about. Does your book talk about varves? I don't know, but I have a slide for it, so we're gonna talk about it. So just an all-encompassing term for all of these various things, which we are now about to talk about. So going on to the next slide, we're going to talk about glacial till. So glacial till is unsorted, meaning you can have large things or small things. See how the guy's standing next to the cliff and there's large boulders and there's gravel and probably sand. It's unsorted. And it's all over the place. It's all mixed together. So unsorted, unstratified sediment dropped by glacial ice. So, you know, it's not like stratified where you've got like big stuff on the bottom, medium stuff in the middle, and then small stuff on the top. It's not stratified, and it's unsorted. Moving on to the next bullet point, the middle bullet point there, the size of material that can occur until is you can have everything from boulder size all the way down to clay size. And clay is super fine particles. And boulders are, well, boulders. These accumulate beneath the ice of a glacier, and they also accumulate at the toe of the glacier and on the flanks of the glacier. And that's your third bullet point there. It accumulates beneath the ice. So if a glacier is melting back, right, and whatever is underneath the glacier's just been dragging everything in the kitchen sink along with it, right? And then when it gets to like the moraines and stuff, where it's melting on the edges, or if it's melting back and it's just dropping whatever it had underneath it, it's going to be everything and the kitchen sink. And this is going to occur in the ice, right? It's different when you start getting meltwater and that starts carrying this stuff away from the glacier. You get some different features. So occurs underneath the glacier, at the toe and at the flanks. Let's talk about the opposite now and talk about stratified drift. So stratified drift, by comparison, is sorted according to its size and weight of the sediment. So looking at the picture below, I apologize that it's rather small. I couldn't find a better photograph though. The stuff up above on the top of the photo is actually very fine particles, kind of sand size, right, particles. And then there's some outliers where you've got some larger rocks mixed in there, but you can see that they're all actually on a line together where all the larger rocks are. So that means that there was just like a lot of water that came through there at that point in time and carried some bigger stuff with it. But for the most part, everything that's on top is sorted into these nice fine lines of like small sediment. And then below it is all the heavy stuff, right? So you've got the gravel. So that is stratification there, where you've got these layers occurring and things are also sorted according to their size and their weight. So the last bullet point though on there is, why does this happen? What causes stratified drift? What causes stratified drift is glacial meltwater carrying this material. So we kind of have talked about water, I think, and how it transport things. I wish I had my sediment jar. But if you are like, say I have a jar of water and dirt in it, and if I violently shake that and it's got gravel and dirt and sand and silt in it, all different sizes of particles, everything's going to be kicked up. Because the water has enough energy that it can carry these things in it. However, as I more slowly shake it and not as violently, the bigger, heavier stuff's going to fall out of the water and fall to the bottom. And if I even just let the jar sit on the table, eventually all of the very fine silt particles will settle out of the water as well. Water sorts things, right? It sorts things because as it loses energy, it starts dropping stuff. It's like, wow, I can't carry this really heavy boulder anymore. I don't have as much energy. And then it slows down a bit more and it's like, wow, I can't carry these medium-sized boulders either. And it drops those, but it, previously dropped the heavier one a bit further back. Now it's dropping the medium one. And then as it gets a little bit further, it says, wow, I'm even more tired. I'm just going to drop now everything that I had, all the small stuff, which is what I have left. So water sorts things. So glacial meltwater causes that. let's talk about probably my favorite type of glacial deposit because they're just so weird, are glacial erratics. So what I want you guys to notice in these photographs below is that there are these incredibly large boulders in all of these pictures. And in 2 of those pictures, there are vehicles for size comparison, how large these boulders are. The top photo on the right-hand side is actually in Eastern Washington, and I have been there on a geology field trip in high school. That rock is actually called Jaeger Rock, and it is a tradition of the high school out in that area to, when each senior class that graduates goes out to this boulder and vandalizes it and puts their, is it really vandalism though? It's nature. And leaves their class graduation year on it. So long-standing tradition out there. You can climb it if you go around to the backside of and have someone who can give you a boost. But you can actually climb that erratic, just go around to the back. It's in the middle of nowhere though, really. So erratics are incredibly large. You can write that on the first bullet point. And on that first bullet point, you can also include that they usually travel with the glacier hundreds of kilometers. So the glacial erratics that are in our state are almost guaranteed going to be from Canada. So the rock there in Eastern Washington depicted, it does not match the local bedrock. That giant thing does not match any of the surrounding rock. It came from Canada. And not matching the local bedrock is what you can write in the second bullet point. So and that's what the term erratic basically means, is it's unusual. It does not match what's here. It's like, saying we have, mostly granite here in this area, right? Which is a intrusive igneous rock, felsic. And then looking at the boulder and being like, well, this stuff is made of gneiss, and there is no gneiss anywhere near here. So that's that. I don't actually know I don't recall the geology of Jaeger Rock and what's around it, but they don't match. So moving on to the next slide, talking about glacial sediments, varves. I actually don't think that your book talks about it, and I want to kind of get through a lecture, so we're going to skip this slide. But they're seasonal. They're deposited at the bottom of lakes, and it's usually very fine sediment. And coarser stuff gets deposited in the winter, and you get finer stuff in the summer, I believe. Finer stuff in the winter and coarser stuff in the summer, in case you are extraordinarily curious. That's all we're going to say about that, though. We're not really going to spend time there. So moving on to the next slide, let's talk about outwash plains. So outwash plains are flat ground that is in front of the glacier. Perhaps it's flat because the glacier once actually extended that far, or perhaps it's flat because it's the middle of the United States. Then everything is flat there. Whatever the reason, it's a flat area in front of the glacier, or it could be a channel, really. Could also be a channel. I see a channel, I think, on the left there. And all of the water that is melting from the glacier is traveling across this plain. And usually we see braided streams on these outwash plains. And that's what you're looking at in that photo, where you have all of these streams kind of converging and diverging. Very beautiful. So let's fill in some bullet points for you guys. What's in it? What is on, well, not in, but what's on the glacial outwash plain? It's mostly sand and gravel sized particles. The glacial erratics don't really get carried by the meltwater. That's how you know a big giant glacier sat where Jaeger Rock is. So it's mostly sand and gravel. Third bullet point that you can add there, or second bullet point you can add there, is that this material is usually graded and stratified. So you've got that sorting going on. And you can then put a comma on there and say that it is usually the gravel and sand that's out there is very abraded and rounded. So the stuff on the plain is graded and stratified, and it also is usually been abraded to give it a round shape. So you get a bunch of round stones out there, not angular stuff like this. You get like, do I have one here? You get like the cobbles that are in most ditches here in Washington. I do. Hold on. Yeah. You get like cobbles like this. This might have been caused by a river, just being carried for a long ways by a river, but because that also can abrade rocks. In any case, you get these rounded rocks. Third thing that you can put there is that this material on the outwash plain has been transported by meltwater. And an outwash plain is kind of somewhat of a depositional feature where you just have this plain that's got a bunch of sand and gravel, and that sand and gravel is graded and stratified. So let's go ahead and talk about some depositional landforms. In addition, we've kind of touched on moraines and outwash plains themselves. And we've talked about, we've also talked to, did I already say moraines? I think I did. We've talked about like, I think that's really it. But anyways, let's go ahead and move on to some other glacial, like just like the landscape that's left behind. Let's not necessarily talk about the material, but just the landscape features that you see as a result. So next slide here, we are going to talk about kettles. Yes, I'm going in order with the book. Good. So kettles, you can also call these, so they're not always lakes. They're like kettle holes sometimes that aren't filled with water, but a lot of times these do fill with water and form what we call kettle lakes. And you can also go and see these on Whidbey Island. There's like almost in the middle of Whidbey Island, there's this part where it really narrows and then it like widens up again. And that particular area is full of these kettle lakes. Controversy though, a local geologist whose opinion is valuable, he actually thinks that they might not be kettle lakes, but they sure look like them. So in any case, let's go ahead and fill in some bullet points for you about kettles and how they form. So these 3 bullet points are the formation process. First bullet point, at the edge of the glacier, you have ice blocks calving off the edge of the glacier. You know, hopefully we've all seen these beautiful videos showing ice falling off the edge of a glacier. They're quite impressive to see. So you'll have maybe not just pure melting, sometimes blocks of it just fall off, right? And they fall off onto the ground in front of the glacier. And then as the glacier recedes and more stuff begins melting and water begins to carry sediment away from the glacier, that outwash might bury some of these ice chunks, because it takes a while for such a large ice chunk to melt. And it can take so long for a chunk of ice to melt that, yes, it can become buried or partially buried by other sediment that is being carried by meltwater around it and whatnot. Just so much stuff gets laid down that it buries it. And then later, these blocks will eventually melt. However, there was a bunch of stuff deposited around these blocks. So when it melts, there's just this hole where the block of ice used to be. And that's what's being depicted there in the bottom picture. So these Reader's Digest bullet point version is ice block calves becomes buried in sediment. Becomes buried in sediment. And then thirdly, the ice melts, leaving a depression behind. So kettles are also Minnesota, where one of my friends is from, has like thousands, I think it is, of kettle lakes. It's called like the land of 1,000 lakes. The state is, just like we're called the Evergreen State. And they're all kettle lakes. So let's go ahead now and move on to the next type of depositional landform. These are all over our state. Drumlins. I actually live on the side of a drumlin. And in parts of Washington where you maybe travel on an east-west road. So a lot of you guys talked about 164th in Linwood being the place where there is an artesian well. A lot of you guys put that in your extra credit bonus point question for the focus question a few chapters ago. And have any of you guys driven 164th before? Maybe? Or perhaps a similar east-west traversing road? You'll notice that you go up these massive hills and then down them and then up another one and then down them. You are crossing over a drumlin. So there's plenty of them here in Washington. They're just all over. We'll actually look at some LiDAR photos of them. The picture there is a LiDAR photo, but it's from, again, the Midwest. So showing Lake Ontario up at the top. Drumlins, let's give you some definitions here. Drumlin, it is an elongated, tapered hill, and it forms under the continental ice sheet. So this doesn't just form under like valley glaciers. It doesn't really form under ice caps. It doesn't form in cirques. These form from the big bad boys that cover an entire continent or large portions of a continent. And we had a continental glacier extend all the way down here in Washington where we live. So that definition that they are elongated, tapered hills that form under a continental ice sheet is actually just for that first bullet point after drumlins. Let's give you some sub-bullet points about that. These hills are asymmetric. So if you look at that photo on the bottom right, you'll see that this hill, side to side, the ridges on either side of this hill are, on the short side versus the long side. Like they're pretty asymmetrical on either side, but as a whole, this hill is kind of like a really long teardrop shape. And that is asymmetrical. So asymmetrical being that first bullet point there. The steep side of the hill, so basically the bottom of the teardrop, that steep portion where it drops off at the end, is usually the up ice part of the drumlin. And the tapered side of the hill, which is kind of like the top of our teardrop shape where it's tapered and it also goes down in elevation, is usually the down ice side of the hill. So we can actually look at drumlins and tell which way the ice was going. What are these made out of? Third sub bullet point there. They are made out of till, glacial till, so unsorted, just, gravel to boulder size material. They're made out of till and clay, also clay. So looking at the diagram in the bottom left, we see arrows showing us the direction of the glacier's movement. And we see that the large part, the high elevated part of the drumlin and kind of the rounded part of the drumlin is facing up ice. It's facing the direction that the ice came from. And then that tapered side that kind of goes down in elevation and forms into like a point, that is pointing in the direction that the ice is flowing. So moving on to some awesome pictures of Washington State. This photograph is it's been colored. These images are normally gray. These are all going to be LiDAR photos that I show you. LiDAR is basically when an airplane flies over the landscape, it's got this like scanner that's scanning the land below it. And then you take that information of the scan that you took of the landscape, of the different elevations of the landscape, you run it through a computer, and this computer is capable, or this computer program is capable of removing all of the trees and the bushes and the grass and buildings and power lines from the landscape. And it produces these images that show just the land. However, LiDAR typically doesn't actually erase, kind of sometimes erases roads, but a lot of times you can still see like freeways and other roads sometimes on these LiDAR images. This image that we're looking at, though, on this slide of the brown and blue landscape, the blue there is water in the Hood Canal. The brown there is the landscape, and you can see that there are all of these hills on this photograph, and they're all lineated, kind of facing the same direction because a continental glacier, glacial ice sheet came down through this area and left behind these drumlins. And if you examine those hills close enough, you will be able to see that the northern part of these hills is slightly larger and rounder and higher in elevation than the southern part of these elongated hills that you're looking at in that photograph. Let's go ahead and look at the next one here. This is a photograph of Home Sweet Home. If you make that image very large on your computer, go ahead and do that now if you would like to follow along. There are red dots on this photograph, and I will tell you what cities those red dots are. There is a red dot at the top, kind of middle left side of the photo. That is Monroe. There is a dot not far from it, below it, on this kind of peninsula that's pointing northward, and that is Everett, where our main campus is. And there's this kind of flat area going through the middle of the photo. That's the Snohomish River and whatever the other river is, and that's its floodplain. But anyways, moving down, there is another dot kind of showing where like Snohomish is. There is another dot showing where like, or no, not Snohomish, sorry. Mill Creek is the is one of, I think, the other dot. I can't remember now. It's been a while. There's another dot, I believe, for Linwood, another dot for like Mount Lake Terrace, and there's a dot kind of towards the bottom of the photograph or the LiDAR image that's near another flat body, which is a body of water. It is Lake Washington, and that, I believe, is like Kenmore, and there's also like a dot for Bothell on there as well. So, anywho, home sweet home. And you can see, though, what I want to draw your attention to is that this landscape also has all of these linear features on it. And these are indeed drumlins all over the landscape. And if you look closely enough, you will see that these kind of elevated ridges all over the landscape do have kind of a more bulbous portion of them, like towards the north, and they're elongated right towards the south, because that's the direction the glacier flowed from the north to the south. Looking at the following slide, this is a close-up showing, let's see, what slide number is this for you guys? Slide 60. This is a close-up of kind of just east of Snohomish. You can see like Highway 9 through there. I labeled it, right? And I also labeled FL in the middle of the photograph. That's Flowing Lake, in case you're familiar with it. I think some of you guys might live out there, because one of you guys said that you were really near the epicenter of the summer earthquake that we had, and that was like near Flowing Lake. And then this picture as well, you can see that there are these elongated hills all over it. This is kind of a bit interesting. If you do go and look at the previous photo, you will see that these lineations on this photograph don't quite match the direction of the other lineations. That's because this portion of the glacier kind of flowed in a different direction than the main continental ice sheet did. So that does happen. Excuse me. We are getting close to being done here, guys. We might not go as long as I thought we would. All right. So let's go ahead and look at the next slide and talk about, we've talked a lot about drumlins because they're all over the area, but let's talk about eskers. We don't have, I don't think we have a lot of eskers out here. I don't know why, but whatever. We don't have many eskers, but we have drumlins to the high heavens. So eskers, there's 3 bullet points here. First bullet point, they are very long, sinuous ridges. And you can see in the photo below, the esker there is just this tall ridge that kind of snakes across the landscape. And it's very long. The rest of the landscape is like flat almost around it. And there's just this one long, tall ridge. And it's like, well, that's weird. Didn't know Mother Nature did stuff like that. Well, it does underneath glaciers. So the second bullet point there is essentially sometimes what you have is you have these tunnels underneath the glaciers. Some people go hiking in them because there are glaciers still today that have these tunnels under them. And people go hiking in them, and it's really cool. Usually in that tunnel, there is a stream. So second bullet point, what you can write is that there are streams in tunnels under a glacier, or sometimes somewhere else within the glacier itself. And within these tunnels, that stream is going to deposit sediment. What kind of sediment is it going to deposit? Third bullet point. It is going to deposit, it's usually gravel that gets deposited here. So something kind of larger, not quite sand or something. It's usually gravel. And so that esker is showing where this stream was that was just channelizing a bunch of material. And, you know, at some point, because it's kind of like this expedited thing, right, underneath the glacier, for expediting like material. And as the glacier melts, right, that sediment is going to get dropped. Especially, I imagine if it's like a tunnel in the glacier and there's sediment accumulating in that tunnel from the stream, and when the whole thing melts, it just like drops this really weird sinuous ridge. I don't know. So that is all the time we're gonna, that's all the time that we are gonna spend on eskers. Let's go ahead and look at the next few slides, which talk about ice in the ocean. So ice in the sea. First type of ice in the sea that we're going to chat about is an ice shelf. And we have many photos here on this slide for you. So an ice shelf, let's get you a definition here on that first bullet point. It is ice atop ocean water. And here's the kicker. And that ice is still connected to ice on land. So what we see in the diagram below is we see the Antarctic ice sheet, and it is very large and it's over the continent. And then a portion of the ice that's been forming on the continent, it keeps accumulating and the glacier keeps spreading out. The continental glacier, also known as an ice sheet, keeps spreading out, and it spreads out over the ocean because it just keeps extending outward. But it's still connected to that ice which is on land. So you can see that kind of extending over the top of the ocean. So let's go ahead and now look at kind of different. We're going to talk about sea ice on the next slide here. So sea ice is different. It is not frozen freshwater glacier that formed from rain and snow melt. Sea ice is literally just that. It is frozen sea water. So sea ice is frozen salt water, frozen ocean. The next bullet point that you can write down on there is that it is not connected to an ice shelf or to land, because it's literally just frozen ocean water. Most of the ice at the, I just kicked the table. Most of the ice up there at the North Pole, there is no continent up there, so it's all sea ice. It's all just frozen ocean up at the North Pole. There is no land below it. So let's go ahead now and chat about, on the next slide, well, what's an iceberg? So an iceberg is not an ice shelf. It's not sea ice. It is a chunk of the ice shelf that broke off. So icebergs, what you can write for the bullet point there is the leading edge of a glacial ice sheet breaks away or calves. We call this calving of the glacier, right? And it calves off and then floats into the ocean. So that's what an iceberg is. It's not frozen, like the top frozen layer of the ocean. It's just ice, a large ice chunk that's broken off of an ice shelf. And most of it is indeed underwater, as we see here. So let's go ahead and that's all the time we're going to spend there because that's all the time we need to spend there. Let's talk about slide 65. And this is the last slide that talks about stuff that's in your book. And then the rest of this is not in your book, and it is a local story. So let's talk about ice dams and glacial lake agassiz. So what is an ice dam? Hold on, I've got a slide. Scroll a bit on my slides. A bunch of skipped slides from my other class. So an ice dam is when you have, it forms when there's some glacial ice that is blocking water from emptying out into a lake or emptying out into the ocean. You basically just, it's just a dam. It's a dam where you dam a river, right? And what happens when you dam a river? You get a gigantic lake behind it. So it is glacial ice blocking unfrozen water from the glaciers. It's blocking glacial meltwater. Glacial ice blocking meltwater. Second bullet point there is that it thus creates large lakes of glacial meltwater. And the light blue colored on the diagram there is showing glacial lake agassiz, which formed during I believe the last ice age. And it was the largest lake that we have found a remnant of on Earth. So it was larger than all of the Great Lakes combined. So massive lake that was blocked from flowing out into the ocean by an ice dam. So glacial lake agassiz, some facts about it. It was 100,000 square miles. First bullet point there. That's a round number for it. I'm not sure if your book gives the same number or if it even has that number in it. Not sure. It formed, let's see, it came into existence about like 12,000 years ago and lasted for about 4,500 years. And that's the second bullet point that you can put on there. And that information is in your book. And then the third bullet point there is that this lake drained abruptly when the ice dam failed. So at some point that ice dam melted and became too weak to hold back the meltwater. And when I say drained rapidly, I mean it didn't take like, years and years necessarily to, it didn't take like necessarily decades to drain it. It literally drained extremely quickly. And we call that an outburst flood, glacial outburst flood. And these floods are massive and very destructive that occurs when an ice dam fails. So let's go ahead and look at the next slide, which is an amazing slide. It has tons of pictures from Eastern Washington. go ahead and study these different pictures and make some basic observations about what are some of the odd things that you're seeing in these photos. And if you would like to sound off in the chat with like, hey, photo in this corner looks like this, or I see this in this photo, you know, etc. I see one comment already that says ripples. Yes, the photo in the top right, that's my right hand. The photo in the top right has what looks kind of like ripple marks, right? But I just want to point out to you guys that there's a small black dot kind of in the middle, bottom middle of that photograph, not quite the bottom, but a little bit down. Do you guys see the black dot? That's a building. And there is a tiny, tiny line that traverses that photograph. Teeny tiny line that goes right next to that building. That's a road, 2-lane road. Lots of kettle-like depressions I see. Yes, lots of holes, right? These ones are not particularly kettles. And I could totally see though why you would say kettle, because we just talked about that. And what I will tell you though is different about these holes is that they're actually holes in bedrock. They're not holes with a bunch of sediment around them. You can't tell that by looking at the photo, but here you are. So yeah, lots of interesting, weird things in this photograph that you don't see every day unless you live in Eastern Washington. Let's go ahead and look at the next photo, and spoiler alert, you are right. Those are ripple marks. And this is a LiDAR image of that top right photograph there showing the ripple marks that feature that spot is called the West Bar. And I was going to go there this summer, but you know what happened to all of our vacation plans. So giant ripple marks that are stories tall, multiple stories high, and miles long. That's weird, right? Like ripple marks that are that big. Oh gosh. And then those giant holes. Well, let's go ahead and fast forward to the next slide, and we will start talking about a Mr. J. Harlan Bretz. We're making Echo homesick. I'm sorry. I don't like being homesick. So a Mr. J. Harlan Bretz. Harlan, spelled like it sounds. And Bretz, B-R-E-T-Z. It's J like the letter J. I found out actually that his name was not J. Harlan Bretz, but that he needed to sound professional. His name was actually Harley Bretz. Because like all the scientific papers that were being published always had like some initial and then kind of nice sounding names, and Harley Bretz. He wanted it to sound more like the names that you see in the papers, and you will find out why. So his interest in Eastern Washington landscapes started in 1910. So interest started in 1910. That's what you can fill in the blank there. Interest during 1910. No, it's not alternatively Harlan J. Bretz. It's just J. Harlan Bretz. So make sure that you get it in the right order. Because it's literally a made-up name that he picked for himself. So he made it J, just the letter J, and then Harlan Bretz. So I don't even know that his middle initial, like, I don't even know that he had a middle name. I think it was just Harley Bretz, not sure. So his interest started during 1910. Next, fill in the blank for you guys is that he was looking at erosional features on the Columbia Plateau. The Columbia Plateau. So in 1922 to 1929, he started being able to actually conduct research in Eastern Washington. There's a whole story as to why he wasn't able to conduct his research when his interest first grew. If you want to learn more about J. Harlan Brett, Nick Zettner did an awesome lecture on him. So his first paper was published, published paper in 1923 on cataclysmic floods or cataclysmic floods carving the channeled scablands. The channeled scablands are basically these massive, it's just this weird canyon-like landscape that we have in Eastern Washington, the channeled scablands. And so after he started studying them in 1922 and then published his first paper in 1923, his hypothesis was that these landscapes were the result of cataclysmic floods carving the landscape. So let's take a look at the next slide there and fill in some blanks on the next slide. So first bullet point there, these were met with huge criticism. This idea of his was met with huge criticism. Why? Why was he so criticized? Let's fill in the bullet points below as to why he was criticized. First reason is because the event that he was talking about was catastrophic. So basically, during that time, that was not a popular idea that there could be catastrophic events that would happen quickly and were devastating to the landscape and drastically, changed the landscape in the giant ways that we're looking at here in these photographs. That just wasn't popular. They didn't like it. So he was met with criticism because it was an idea that involved something catastrophic. Second bullet point, the geologic community at that time knew very little about Eastern Washington. So the geologic community, which he was talking to, who were criticizing him because they didn't know anything about it. They'd never seen it, and they hadn't studied it. No one had really been studying it before. And it sounded like a crazy idea. They didn't know what he was looking at, so they just called him crazy. That doesn't sound fair to me. And then the third reason why he was heavily criticized for his idea was that he was not an Ivy League elite. So he didn't go to an Ivy League school. He didn't, I don't think that he even necessarily had a degree in geology. I can't recall, but he was very interested in it, to say the least. So he was not an Ivy League elite. And this is a trend throughout history in geology, is that people who aren't like part of the in crowd and have these radical ideas about like glaciers or other geologic processes, they are not accepted for a long time. But they may come to be accepted sometimes, as is the case with what we are talking about. So anyways, it's worth mentioning that J. Harlan Brett had a sidekick. This is the bullet points there in the lower right-hand side. He had a sidekick, a Mr. Joseph Pardee. And J. Harlan Bretz was finally vindicated in 1950. What do I mean by that? I mean, he released his idea in 1923 that these must have been caused by cataclysmic floods. And it wasn't until 1950 that his idea started being accepted as actually true. And this is a glacial story, by the way. But even still, after 1950, there was still a large debate around it in the geologic community. And that debate lasted for like about 40 years. So I believe start to finish, it was still 10 years after 1950 before he was really totally accepted by everybody, or his idea was. But now if you go to Eastern Washington, like say Dry Falls, you'll actually see a plaque there about J. Harlan Bretz being right. Sorry, it's an underdog story, and I love an underdog story. I'm not necessarily about conflict, but like I feel for these underdogs who end up being like ostracized and not seen, basically just ostracized, and are like, you can't be right. You don't know what you're talking about. And it's like, maybe you guys should listen, because maybe this new radical idea could be true. And look into it. I don't know. I'm about that. So let's go ahead and talk about, I don't really have a bullet point for this, but basically J. Harlan Bretz was right. What was the case? What was going on? Well, first I'll go to the next slide. There's a quote on there from J. Harlan Bretz, and this story is tied to the Lake Missoula and the Missoula floods, which is why they're all titled Missoula floods, all the slides. And J. Harlan Bretz's quote is that ideas without precedent are generally looked upon with disfavor, and men are shocked if their concepts of an orderly world are changed. So basically, people who have long-standing ideas don't like to hear that they're wrong. It's kind of what it comes down to. And I mean, why wouldn't you? Like, if you dedicated your life to a certain way of thinking or to a certain hypothesis or theory, and then some young guy who's maybe like, who hasn't been part of the community, who you've never heard of, who may not even be very well educated, or didn't go to, maybe educated, but didn't go to an Ivy League school, or maybe isn't even in that career path, comes along with this radical idea and tells you like, you've been wrong your whole life. Everything you've dedicated your life to. Yeah, I think it's wrong. What research scientist is going to want to hear that? Nobody. For my master's degree, I was about to get a null hypothesis, and I knew some people who got null hypotheses. And when you dedicate like even just 2 years of your life to researching something and then find out that it's not true, it's devastating. Especially when you're trying to earn a degree for it and you just want to cry. Like, it's very devastating. And not that that's not valuable. It is still valuable. Just as like a person who spent, like 2 years of your life working on it, to get a null hypothesis is just, you want it, you want your idea that you don't want to feel like you wasted your time, I guess, but it isn't really time wasted. But it feels like it at that moment in time, and then you're really upset about it. But it's not wasted time. But it sucks, it's really rough finding out that like your idea, like maybe there is this crazy idea and it kind of is not in line with what you're hoping or have dedicated your life to. So anyways, there's that. Literally sometimes in like scientific communities, when someone has like a new idea and it is like a good idea, in fact, it's better than anything that's come before it, you'll try submitting your research papers, right? Like to get them published in a journal. And there will be that one guy on the publishing, the review committee for that scientific journal who's like older and stuck in their ways and is like, no, that couldn't possibly be the case. And everyone's like, dude, the evidence lines up. And they're like, no. And then their paper doesn't get published. And sometimes people just have to like retire from these committees in order for like stuff to get published. So that's crazy. But anyways, let's go ahead and take a look at finally like our grand finale slide to this story. Slide 71 there. The white at the top of the photo is, oh, that's the name I've been trying to remember for forever, is the Cordilleran ice sheet that came down from Canada and extended into Washington, Idaho, and Montana. Other parts of ice sheet from Canada also extended into parts of the Midwest and like leaving all those moraines and Kettle Lakes, etc. And you can see the Puget lobe there. There's like this lobe covering the Puget Sound. But what I should really be drawing your attention to is where that red arrow is pointing in Idaho. And we see that there's just this bit of ice that's come down into Idaho, and it is blocking all of this meltwater in Montana. And in Montana, we then formed Lake Missoula, named for Missoula in Montana. And yeah, so basically this water couldn't find its way to the Pacific Ocean, and it was very upset and because it was being blocked, and a bunch of it backed up there, and eventually that ice dam failed and an outburst flood occurred and carved all of the kind of brownish area that you see in Washington. So it literally like carved out. And if you go to Eastern Washington and you see these canyons, like anybody of you guys who are listening been to the Gorge in Vantage, Washington, maybe you went there for a concert, a very popular concert venue, or perhaps you've driven through Vantage in the Columbia, gone over the Columbia River, and there's like all these massive gorges and canyons in Eastern Washington. Yeah, and they were carved. Those are all carved by the meltwater that was dammed up, just rushing through that area. And it made things like potholes where there was like a rock that sat in the land and like carved it out. And these potholes are like the size of like college buildings. They're insanely huge and made the ripple marks on the West Bar, right? Also made gigantic waterfalls, things like that. So yeah, and it's also worth pointing out to you guys that this didn't happen just once. I'm not sure how many times it is believed that this happened, but that ice dam kept growing back and kept failing. And we kept flooding Eastern Washington and ravaging it over time. So yeah, there you have the big picture of what J. Harlan Bretz was on to. Slide 82 is just kind of a brief, I don't know that your book talks about this. I don't think it does. But I wanted to like point out to people because people often sometimes wonder like what causes ice ages, what causes this cycle where we get massive like ice earth and then we get like not ice earth, these glacial and interglacial periods. Well, they're called like Milankovitch cycles, And Earth doesn't have a perfect circular orbit around the sun. It's actually got some eccentricity to it. And I believe, and the Earth also has like a wobble on it, right? And I believe that through time, sometimes our orbit has been more eccentric and less eccentric. So it's all of that stuff that causes ice ages, is our orbit being more eccentric or less eccentric, and also the fact that the Earth's axis has kind of, tilted on its axis. So right now, what are we at right now? We're at like a 22, I think, degree tilt or something like that. I'm not sure what our current tilt is of the axis around which our planet spins. It's not actually perfect like this. However, it does wobble. And then coinciding with the eccentricity of the orbit of the Earth around the sun and how far, the Earth is tilted, that will cause parts of the Earth to get really, really cold and form lots of ice. And there you have it. Will we have another ice age? Well, these cycles do happen throughout Earth's history. So if Earth stays here and if we don't mess it up too badly, yes, it theoretically should. So yeah, that's that. That's lecture for Glaciers. All right, we ended at 4:45. Yay. Does anyone have any questions that they want to ask? I know I'm super behind on grading. I've been such an awful person. I'm so sorry for you guys. But I am working on grading. If you guys have any other questions, though, oh, shoot, I was going to make an announcement. Next week is actually our last week of class, and we don't have a finals week. So us teachers are put in a really unfortunate position where we have to use our last week of class for finals week, which means that we are short a class day, and none of us teachers are excited about it. So basically, we're going to do next week, our next lecture will be our last lecture. It's going to be about deserts, and it's going to be kind of a mini lecture covering the second half of the book, the second half of the chapter, not the whole book, but the second half of this chapter that we're talking about, Glaciers. And it is going to be a mini lecture. We won't go too heavy on it like we do Glaciers. I happen to know a lot more about glaciers, and I'm able to teach more about them than deserts, despite living in one. So, yeah, we'll do like a mini lecture. There will still be a lab for deserts, and that will be due Friday. However, the final is going to be on Wednesday, during when we would normally have class. So it's going to be Wednesday at 3 o'clock as usual. And it will be a little bit longer because it is cumulative. So there will be a few questions about previous chapters that we covered on the previous two exams, but there will be a heavier focus on earthquakes, on glaciers, and on deserts, because those are the most 3 recent chapters. However, there will be still several questions, not as many, but there will be several questions about some of the previous stuff that we learned. And remember that the most important stuff that we learn in this class is hazards and emergency preparedness in regards to geologic hazards. So definitely study up on hazards and geologic hazards, as well as like the scientific method and minerals. Wow, that feels like ages ago. Minerals and rocks and everything. So, and it will be open everything as per usual. It might have a stricter time limit than this last exam did. And what that means is that you want to take notes, and you do not want to rely on Google to find your answers, because the information on Google isn't necessarily the information that's in your book. It might not be specific enough, or it could be just wrong, and you won't get full credit for something that's not specific enough to, like, specific to our book. So yeah, that definitely means with the stricter time limit that you're going to want to actually study up on past material and make sure that you know that. And I do highly recommend notes, taking notes, because like even just rewriting a page of notes or two, like just some of the things from all of the chapters onto like 1 or 2 pages, is incredibly helpful in preparing you for an exam. So yeah. Anything else I want to say? It'll look just like the other exams, with some visual questions, some multiple choice, some short answer, some long answer, fill in the blank, all of that. There will be probably a few, 1 to however many, but not too many questions where it's like, look at this property. Do you want to move here? What geologic hazards might be associated with it? Because those are fun questions. Those are practical questions that you can actually take with you from here and use them. So yeah, that being said, I think that's everything. Emergency kits have those if you want the 10 points extra credit and haven't done an emergency kit yet, you can still do that up until next Monday. Yeah, so let's see. Focus questions I might have due by Wednesday for deserts, because the focus questions are to help you study. So it's not very useful if you don't do them until after the exam. So I will probably have the focus questions also due on Wednesday, because I want you to do them prior to the exam. So I'm going to force you to do them prior to the exam, because we all just need that sometimes. Yeah. So thanks for listening. End of lecture. I see that Noah wants to join a live chat. If anyone else would like to join a live chat, please leave your name in the comments area, and I will send an invite to your email to join a Google meeting, and you'll just go to your student email, see the email from me, and click the link in it, and it should take you to the Google Meets. Yeah, have a good evening if you don't want to do the Google Hangouts. Anybody else want to join the Google Meets? I'll start getting that set up. Oh, excuse me. It's that late night moving, helping my friend move. All right, well, I don't see any other requests for a live chat, so I will end the live stream for now, and have a wonderful weekend. Bye.